My good friend George Curtis is separating light from an argon source into its component frequencies with a spectroscope. Under high voltage, some of the argon atoms in the tube become ionized, and free electrons, accelerated by the electric field in the tube, collide with neutral argon atoms, causing them to undergo excitation. Excitation and de-excitation produce colors unique to argon. No other gas emits the exact same color. Here's what occurs in a spectroscope. In this diagram, the light source is an arc lamp that emits white light. Rays of emitted light pass first through a lens, then through a thin slit, through another lens, and into the prism where different frequencies of light are separated. A grating can take the place of the prism. Spectroscopes commonly have either a grating or a prism. Here's a view of various tubes of gas being excited and emitting their characteristic colors. We have helium, neon, argon, krypton, and xenon, all glowing due to voltages across the ends of the glass tubes. A spectroscope focuses light from the constricted regions in the middle of the tubes. A spectrum is produced for each gas. Each color is focused at a definite position according to its frequency and forms an image of the spectroscope slit on the screen or appropriate detector. So each line on the spectrum is an image of the slit on the spectroscope. We see the spectrum for helium, for neon, for argon, for krypton, and for xenon. Each spectral line corresponds to the electron transitions between atomic energy levels. Actually, there are many other lines, often too dim to be seen with the naked eye, and some outside the range of human vision. Spectral lines are as characteristic of each element as are the fingerprints of people. The spectroscope, therefore, is widely used in chemical analysis. When the light source is white light, the spectroscope produces a spectrum over the whole rainbow of colors. This, like the spectra of light-emitting gases, is an emission spectrum. Now here's something very important and interesting. If a gas is placed between a white light source and the spectroscope, we choose sodium vapor here, careful inspection will show that the spectrum is not quite continuous. There are dark lines distributed throughout the spectrum. What we have is called an absorption spectrum. The dark lines are absorption lines. What's happening here? It so happens that atoms absorb light as well as emit light. An atom will most strongly absorb light having the frequencies determined by its quantum nature, some of the same frequencies it emits. When a beam of white light passes through a gas, the atoms of the gas absorb light of selected frequencies from the beam. This absorbed light is re-radiated, but in all directions. So the beam of light that reaches the prism is weak in these re-radiated frequencies. That accounts for the dark lines in the absorption spectrum. Now, if no light was absorbed on the way to the prism, the spectrum would be continuous. If we substituted a white light source with some glowing gases, we'd have emission lines. An absorption spectrum for the same element shows dark lines where emission lines would be. The dark lines are like emission lines in reverse. Quite remarkable, or equivalently, quite yum. Although the sun is a source of incandescent light, the spectrum it produces upon close examination is not continuous. Not quite. There are many absorption lines called Fraunhofer lines, named after Joseph Lines. Hey, I'm just kidding here, as they're named after Joseph Fraunhofer, the Bavarian optician and physicist who invented the spectroscope and first observed and mapped the dark lines accurately. At about the time spectroscopes were gaining popularity, the famed philosopher Auguste Comte cautioned on expecting too much of science. Humility was in order. For science can't tell us everything. And as an example, he stated that mankind will never know the chemical composition of the stars. But then absorption lines were found in the spectra produced by the stars. These lines indicate that the sun and stars are each surrounded by an atmosphere of cooler gases that absorb some of the light coming from the main body. Analysis of these lines reveals the chemical composition of the atmosphere of such sources. And intriguingly, stellar elements are the same elements that exist on Earth. An interesting sidelight is that in 1868, almost a half-century after the discovery of the spectroscope, spectroscopic analysis of sunlight showed some spectral lines different from any known on Earth. These lines identified a new element, which was named helium, after Helios, the Greek god of the sun. Helium was discovered in the sun before it was discovered on Earth. Is that yum or what? And there's more. Determination of the speed of stars is made by studying the spectra they emit. A moving light source, like a moving fire engine, produces a Doppler shift in frequency. Sound for a fire engine, light for a star. The frequency of light emitted by an approaching star is higher, while from a receding star is lower, compared with a stationary source. A shift in visible spectral lines is toward the red end of the spectrum for receding sources. Almost all the galaxies show a red shift in their spectra, evidence that the universe is expanding. Later we shall see how the spectra of elements enable us to determine atomic structure. For now, I want to leave you with a question. In viewing the edges of a star, how can a spectroscope be used to measure its rate of spin? Think about that. Until next time, good energy.